Welcome back to Chapter 4, Section 1, Exponential Functions and their Graphs. So in this video, we're going to define what an exponential function is and learn how to graph exponential functions. So an exponential function is a function that exhibits geometric growth, which we call exponential growth. An exponential function is defined as f of x is equal to b to the power of x. This is the parent function. So parent function is the parent exponential function. So we've got two things. Notice that b, it's a number, and then x is our exponent. Since x is an exponent, that's why these functions are called exponential functions, because the variable is an exponent. So x, the exponent, can be any real number, and b is a growth factor. The growth factor is such that b has to be, there's some conditions that apply to b. B has to be positive, it can't be negative, and b cannot equal 1. So b is the growth factor. It is the number, so it's growth factor. It is how much the output gets multiplied each time that the input increases by 1. So back here, when we were looking at geometric growth, this times 2, 2 is the growth factor. When x goes up by 1, the output gets multiplied by the growth factor of 2. So the base is your growth factor. The base just so happens to be equal to 1 plus r, where r is rate. R is the growth or decay rate. Now, if the rate is less than 0, so if the rate is negative, that means that your exponential function is going to be decaying. And that's like this one, carbon 14. The function's going down. The growth rate is negative, and that means that the growth factor is going to be less than 1. If the growth rate is positive, then that means that the base is going to be greater than 1 because you add the rate to 1 to get your growth factor. And that's when things are going to be growing exponentially, like the population of the Earth since 2000. So here we have growth. The base is greater than 1, and the rate is greater than 0. Remember that the base is equal to 1 plus r. Over here, down below, we have decay. Decay, I can't spell it. The base in this exponential function is going to be less than 1 because the rate is negative. The growth rate is negative because whatever the carbon 14 is getting smaller. And remember, the base is equal to 1 plus the rate. So if the rate is negative, our base is going to be less than 1. So those are the two situations that happen with exponential growth. We can have growth or decay. Base is greater than 1 with growth. Base is less than 1 with decay. Growth rate is positive with growth. The rate is negative with decay. We're always whatever you're measuring is decreasing. It's losing. So remember, when the variable is an exponent, it's an exponential function. How do you evaluate exponential functions? So here is an expression, the algebraic expression of an exponential function. And let's just see how to evaluate manually, numerically, this function. So we have an xy table. So when x is 2, f of x is equal to 9 to the second power, which is 9 squared, which is 81. That's nice. When x is equal to 0, f of x is equal to 9 to the 0, which equals 1, because x to the power of 0 is equal to 1 for all values except 0. 0 to the 0 is not defined. We can have fractional values in our exponents. 9 to the 1/2. Remember, fractional exponents, the denominator is a root. So it's the index of of the root, so the denominator becomes that index, it's 2. So really this means 9 to the 1/2. It means the square root of 9 to the first, which is the square root of 9, which is 3. Then we've got negative. We allow negative exponent values. 9 to the negative 1. Remember, when the exponent's negative, you take the whole expression, you move it to the denominator and change the sign of the exponent. So 9 to the negative 1 is the same as 1 over 9 to the first, which is simply 1/9. 9 to the negative 2 is equal to 1 over 9 squared, which is 1 over 81. That's how you evaluate exponential functions. Sometimes there are going to be exponents that you can't evaluate manually, and that's where graphing calculators are really, really, really handy. So let's go to a graphing calculator and see what those look like. So here's our graphing calculator. I'm just going to put in 9, and I want to evaluate 9 to the 2.5. So I type in my base 9. To get an exponent, I hit this button that looks like a little rooftop, which is the technical name for it is caret. And then I'm going to do 2.5. So 9 to the 2.5 is equal to 243. If I want to do 9 to the 0.01, do the same thing and I get 1.0222. If I want to do 9 to the negative 3.049, I type it in like that, hit enter, and I get a value. So you can use this feature in your graphing calculator to evaluate. We're going to be using to evaluate exponential functions. There are other features, ways you can evaluate exponential functions using a graphing calculator, and we'll get more into those later in this unit. But we will be using graphing calculators in this unit, so please bring it to class. Okay, so how do we graph exponential functions? Let's look at exponential growth. So here's our function. F of x is equal to 2 to the x. The base in this expression, in this function, is the number that the variable x is stuck to. So here, find the variable x. That tells you what type of function. It's an exponential function. Then we find the base. The base is 2, because 2 is what the exponent is attached to. So our base is equal to 2. And that is also equal to our growth factor. So every time our input goes up by 1, the output gets multiplied by 2. Now let's figure out what the growth rate is. Remember that the base is equal to 1 plus the rate. So since our base is 2, that's equal to 1 plus r. So our rate is equal to 1. So a rate of 1 doesn't seem like it's really interesting at all, but if we change the rate to a decimal, so let's do 1 times 100 over 100, and that's going to be 100%. So the function is going up by 100%. The growth, the percent change is 100% each time. So that means it's doubling. Kind of crazy. Let's plot this and see what happens. Let's create a table of points, x and y. And for x, let's just do, like -2, -1, 0, 1, 2. So 2 to the -2 is 1/4, 2 to the -1 is 1/2, 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4, 2 cubed is 8. Then we can plot these points. -2, 1/4, -1, 1/2, 0, 1, 1 up 2, over 2 up 4, over 3 up 8, and we get these points. And as x increases, y is clearly increasing. And you can see the growth factor going on here. 1/4 times 2 is 1/2. Times 2 is 1/2. 1/2 times 2 is 1. 1 times 2 is 2. 2 times 2 is 4. So you can see the growth factor when you look at the numbers that go with this function and numerically in an XY table. But what's happening? Well, actually, so we can graph the function here. We know it's going up and up and up and up and up like that. But what happens down here as x gets smaller and smaller? Well, let's break out the calculator and see what happens. So where's my calculator? Here we go. So I'm just going to do, let's see, I'm just going to do a function clear. I'm going to enter my function here, 2 to the x. I'm going to enter it there. And then I'm going to use tables. So I'm going to do second window to get to table set. And my starting value, I don't really care where that is, but I want the independent variable to be ask and the dependent variable to be auto. And I quit out of that, and now I'm going to go to table. So I hit second graph, and that gets me table. And this is all old data. So clear, actually enter. So if I do, let's see, let me just scroll up here to the top. I can't do that. Okay, so I'm just going to do like -10. So this is going to do 2 to the -10, and that gives me 9 times 10 to the -4th. If I do 2 to the -9, I enter the exponent in my x, and then the calculator does the work. 2 to the -9 is 0.02. 2 to the -8 is 0.04. 2 to the -7 is the 0.008. 2 to the -6 is 0.015. 2 to the -5 is 0.03. 2 to the -4 is 0.0625. To the -3, and to the -2, and to the -1. And you can see what's happening here. As the x values are decreasing, the output value is decreasing. Let's try -1,000 and see what happens. And what happens is we get a number that it says it's 0, but it's not really, because 2 to the -1,000, that's going to be 1 over 2 to the 1,000. That's going to be a really small number, but it's not actually equal to 0. So what we're seeing here is asymptotic behavior. As x decreases without bound, the function output, it's approaching 0. And the reason we see 0 here in the table is because of rounding error in the calculator. The calculator can't express a number that small even when it uses scientific notation. So what's happening here, we can draw on our graph, is we have a horizontal asymptote at, that is the y-axis. And that's our function. So there's our smooth curve. And the domain of our function is all real numbers, because we can have rational and irrational exponents. The range, it's going to be from just above 0 all the way to positive infinity. And we can see that here in our table. Now let's look at the end behavior. And we can say that the limit of f of x, I think that's our function name, as x goes to -infinity. So as x goes to -infinity, f of x is going to 0. And then the limit of f of x as x goes to positive infinity, there should be a negative there, as x goes to positive infinity. So what's happening to f of x as x increases? Well, f of x increases without bound. So that end behavior, it's asymptotic on one side and it's growing crazily in the other direction. So we have this horizontal asymptote that is the x-axis, and the equation for the x-axis is y is equal to 0. Notice that this function is 1-to-1, so its inverse is also a function. Also notice that this function is constantly increasing. It's only increasing. This function is never decreasing. When the growth rate is greater than 0, the function is always increasing. It increases from -infinity to positive infinity, and the function never decreases because it's always growing, never decreases. So these are really interesting functions. They're always growing. Well, when the base is greater than 1, it's always growing. That's how you graph an exponential function that has a base greater than 1. So I'm going to end this video, and in the next video we'll graph an exponential function with a base less than 1.